I don't really have any business things to remind you guys of other than normal stuff. Final projects are in the oven, I hope, and creativity projects. You guys know to turn in missing assignments. Do not fail this class, please. It will be very tragic for me to type that F into your student portal. All right. Yeah, you have time to still work it out. So, any questions about anything like business related, anything like that? All right, cool. I got my contacts prescription updated this morning, so I can see everybody in the back of the room finally, which is really exciting. Since you guys refused to huddle up around the front, now I can see you. All right, what's going on? What did we do last week? What's happening? Questions, concerns, and thoughts, and worries? Yes? Yeah, I mean, well, what are you going to do otherwise, right? Yeah, it's kind of cool. So we're going to start looking at other galaxies. We're going to start building out a formation model for them today. We're kind of in a whirlwind at the end, so we have today 2, maybe 3 more classes to really put a bow on this whole thing, and we haven't totally made it to the Big Bang, and I want to make sure I spend some time on that because it's kind of where all of this that we've been struggling to comprehend builds up to, is this giant theory of everything in the cosmos. So yeah, we have to model things based on what we can see outside of ourselves, and that's how we, in some sense, derive what we think about the place that we're inhabiting as well. What do you got, Mia?
I can't remember if it's from one of the lectures or from the workshop, but looking at how the further other galaxies are away from like our galaxy or Earth, the faster they're moving away.
Ooh, we'll get there.
Which is interesting.
We'll get there.
But, okay.
Yeah, we need to talk a little bit about why people think that. And it's not quite as clear cut, but that is certainly, I think that's what we'll get to by the end of class today. Hey. But yeah, that's kind of building up to the idea, because of course if the galaxies, and we may as well preview it right now, but if the galaxies are all moving away from us, then it seems like, what are they moving away from? And of course that's one of the second, there's kind of 2 big pillars for this Big Bang idea, and one of them is this idea of the galaxies moving away from us. So we'll talk about why people, we'll build towards why people think that. And just to give away the punchline, it's because of course those galaxies that are farther away seem to be redder in light. And redness, if you guys recall, all the way back when we talked about Doppler shifts, we talked about how sound sources, that are moving away, you get a lower frequency, right? This is the ambulance moving away from you on the highway or whatever. Same thing with light. So there's an argument to that end, and it's actually not treated necessarily as a speeding away velocity at this point. It's actually treated as an actual expansion of the universe, which is a really far out idea. And we will play with it and its alternatives by the end of the class today. So I'm glad you brought that up. Yeah.
I thought it was also really interesting that we talked a little bit about how galaxies move and how it moves in one big unit instead of how we thought that they transform.
Yeah, that's called the galactic rotation problem, which I think is one of the biggest local issues in astrophysics today that people are really concerned about. Because the normal gravitational equations don't quite work. Although the stars closer to the center of the galaxy seem to be moving faster, they're not. It's not quite the same way a solar system would work out. It's a little bit off. The stars farthest away from the center are also moving at quite a click, a little bit too fast, quite a bit too fast actually. So that's pretty weird. And of course, what are the options for that? We talked about dark matter, this some sort of invisible source of all this gravitation that's holding the arms in place outside of the galaxy. It's a real conundrum. I mean, you need to either have a gravitational source, or you need to have some cohesion amongst the different star systems that we haven't understood yet. I think there might be possibilities in each one of those bins that don't involve magical new substances either. And we talked about like the cold dead stars as a possibility. We talked about this kind of velcroing together of star systems through the heliosheaths as well, which is an interesting idea. What else, guys? Yeah, Summer.
We went over
brief history of our understanding as a species of what the Milky Way is, and that ranged from Anaxagoras and Democritus proposing that it was a bunch of stars between 3 and 500 BC, to the Aristotle thinking it was just something in our atmosphere, to a few Persian astronomers who believed it could be baby stars or full-size stars.
Yeah, it's kind of interesting that the idea that it was a bunch of stars was proposed and then abandoned for 1,000 years, and then not really accepted by the West for another 1,000 years. Yeah, it's kind of far out how that can happen. I mean, even the idea of the atom, perhaps the biggest scientific concept of all time, was proposed in a poem, 2,500 years ago, Democritus, and essentially the idea that the physical reality would be made up of some sort of indivisible bits is really what they meant. So I don't think they meant the atom the way we think about it with the electron shell and all of that, but just the idea that physical reality would be reducible to moving pieces. And of course, depending on who you talk to, that's been largely abandoned to the point particles and this idea of fields today, which is maybe beyond the scope of our conversation. But these things are trendy. They go in and out. Sometimes the trends last for 1,000 years. Sometimes they can change overnight. It's a really wild ecosystem of ideas. What else, guys? Yeah.
You briefly mentioned the solar winds in regards to the Helio sheet, and I was wondering if one of your notes on that in your work is you finished up in briefly again us, and then also how you described it as Velcro possibly, and I was wondering if you thought that would work on any other levels, like atomic or galactic or anything.
Yeah, 100% I do. So I had a really interesting, I know you guys are you guys too young to listen to podcasts maybe? So, I don't know. We do these really long-form conversations with scientists. My wife and I do this podcast. And we had a really cool conversation with this Princeton physicist named Eric Zernstein, who studies the Helio sheath. If anybody wants to check it out, you probably just search our podcast, Demystify Sci, and Eric Zernstein. We get into kind of the weeds about that. So it's very much even the number of people that are even studying the Helio sheath is really small. So we know that basically when the solar wind is kind of like this fire hose that's just spraying matter off, essentially ionized hydrogens off the surface of the sun. Presumably all the stars are doing this. And as it crashes into the interstellar medium, it forms a kind of what they call a bow shock. It's basically what you would imagine, there's basically a bubble between those two pressure interfaces. And it's really poorly understood what that does to the matter at that interface. If it actually forms magnetic structures that could be tangled up with the star systems next to them. It's brand new science. Actually, the study of magnetic fields inside of galaxies is brand new too. And we talked to this Stanford astronomer named Lopez Rodriguez, who was one of the first people to study the presence of galactic magnetic fields as a player in organizing galaxies. So I think we're going to start to build out this formation model for how people think galaxies form, but it's largely based on gravity, which is totally reasonable because that's predominantly how our own solar system seems to function. But could there be other things that are knitting things together, like electromagnetism, like frictional interactions between these streams? Absolutely. It's just so brand new. It's just hard to... the other thing about galactic magnetic fields is they're ugly. They're not these really beautiful... you think about a bar magnet. It has a nice toroidal magnetic field, very beautiful. The galactic magnetic fields are messy, right? They're just tangles of... each arm of the galaxy has multiple sheaths of different polarity of magnetic fields. So yeah, needs more work. I think that'll be promising in the future. I think that the increasing failure to detect dark matter will really revitalize the search for alternatives. And so far, not even really theoretical proposals for what dark matter could even be. So yeah, I think it's an exciting time for all this stuff, in so much as you guys find it interesting. There's so much work to be done. It's a really fresh field. What else, guys? Yeah.
We talked about wormholes a bit, just how
Wormholes.
science fiction affects like actual science and like how black holes also like can't actually do gravity bending, or there's a lot of weird science about it. That's not it.
Certainly not consistent with the gravitational lensing. Yeah, I mean, I don't want to keep like beating that horse. I feel like I've beat it dead already, but there is a deep, deep need for us to witness things that are, in some sense, speak to something beyond this atomic, physical plane of existence that we're all both familiar with, but sense that there's something more to it, right? I don't know what more I can say about that without boring you guys to death, but there's certainly a level of existence that has nothing to do with atoms that we're all very familiar with, and it's probably the most important one in our normal lives. Of course, you got to pay attention to atoms too. You don't want to get hit by a bus or something, but at the end of the day, there's a lot going on that physics probably isn't the best tool to shape and to understand that side of the world. So, I don't know, it's kind of an interesting arbitrary distinction that for some reason physics ended up with the keys to the castle with cosmology, and people more now than ever expect physics to have all the answers for everything. And I don't know, do you guys think that's an unreasonable ask? That physics should be able to explain everything? You think physics can explain love? Well, I mean, here's the question. Do you think that, I'm just picking on love because it's a very profound, deep experience that we've probably all had, right? Whether for a spouse or for a family member. But it's like, there's things that happen in the universe that just don't seem to really have much to do with physics at the end of the day. So, and I don't know if they're worth writing out of the equation either, which is really interesting. What do you guys think? Don't be afraid. Yeah, Mia.
I also think that it can't, because how we've been talking about the stories are consistently changing, and even if the mathematics lines up, it doesn't always make it true.
Yeah, that's the hardest part.
If physics was to explain everything, there's no room for growth and change.
Yeah, it's such an interesting conundrum that a statement could be mathematically true, but still lack explanatory power. I can't think of a better example than what we talked about with heat, right? Because heat was treated as a fluid for many, many, many years, even when they were building engines that were super functional. But heat's not a magical fluid, right? So even if we're able to model those interactions with the galactic rotation as dark matter, and it's some sort of undetectable magical fluid, doesn't necessarily mean it's true. It just means that it behaves that way, that's a hard one to even get on the same page with people who study this stuff professionally. We become very, very proud of our precise equations, and we should be. They allow us to go and fire rockets into orbit and do all sorts of incredible stuff, but it's not quite the same as explaining how things work, to be able to describe how things go. You got the most gentle voice, Michael.
Yeah, you have a different perspective on a love thing. I'm very clinical with that, where it's just an evolutionary mating behavior. Oxytocin, dopamine.
I agree. It is a behavior, but our behavior is fundamentally physical. Because the behavior is a really complex abstraction, right? It's like, you're definitely you're made out of atoms, right? But, I don't know, it's just, there's something about, all right, so, personal example, my sister-in-law's cat died yesterday. And they sent us a picture of, the dead body of the cat. And it's really sad because she's staying with the parents, the cat's staying with the parents, the sister-in-law's in India right now. So they took a picture of the cat. And it's weird because it looks like the cat, but you can tell the cat is gone, right? And so what is that's gone? What is it that's there when the being is alive? All the atoms are still there in the cat, but something's profoundly different about it. It's no longer animated with the fill in the blank, whatever you want. Consciousness, the spirit of the cat, whatever you want to say. What is that? Is it a physical thing, or is it something more abstract and metaphysical?
The Rube Goldberg machine of that organism has stopped.
The motion is what we refer to with the being, though, right? It's the motion, and so while the motion certainly depends on the physical actors, right? You can't have motion without physical actors, but there's something almost there's something beyond the atoms as well in that motion. I don't know. I think that in a different, like on an Earth, maybe 1,000 light years away, if there's another Earth and there's people like us sitting around, or there's scientists working in some ivory towers somewhere, I think it could be a very logical deduction to have the biologists studying the stars as well, and looking at something like galactic rotation and being like, well, the thing is clearly a being, and it's moving because beings move in ways that can be explained behaviorally and not explained based on their atomic interactions per se. Like a biologist would never try to explain a behavior purely based on atomic interactions. They might say that it's playing out on these atoms, or that there's these transmitters involved in the signaling between the cells, but I don't think that a behavioral biologist would start there, basically. And perhaps it's not the right lens to apply to the stars either. I don't know. I'm just throwing it out there. Food for thought. What do you guys think? You guys look like all your cats just died yesterday too. Good grief. The cat was old. It's all right. Everything must pass. All right. Do I need to pick on some people? What's going on? Is Jaden here? Mercedes, I see you back there. Got any thoughts for us?
I just jotted down, talking about like the center of the galaxy, and it being the Sagittarius A.
What do you think about Sagittarius A? What do you think about the super black hole at the center of the galaxy?
I'm curious to see how it like develops.
Is it an appealing idea too?
Kind of. I just want to see like what. Like I don't want to see what happens, but like I want to see.
Yeah. Fair enough. Yeah, it's is there any, so here's the thing. I think, well, I'm just kind of curious. It's hard to poll people because you guys are all worried. I'm not going to judge you, but I'm curious, like, how many of you really enjoy that there's a supermassive black hole at the center of the galaxy, and how many of you are unsatisfied with that idea? Which one?
I'm unsatisfied.
Right.
Like I was telling you last class, like I watched that video that NASA created, going into it, what it feels like, what it looks like in there. I feel like we're good just chilling here. Like, I like our planet and stuff, but we don't have to get sucked into the black hole. But I feel like it definitely needs to be explored. I feel like we definitely just got to toss somebody in there. Like GoPro or something.
Amazing.
Or I could go in there. Like, I'm down to go find out too.
Well, I'm
I'll take
sure
a little,
that they will.
scientific sacrifice for us, you know?
I mean, it's going to be really boring if somebody sacrifices themselves and it's just
But what if I
monotonous
just go
boredom.
and I'm just in a different galaxy.
Then I will eat my hat.
That'd be pretty
It is a cool idea.
It's a cool
I think it's almost a irresistibly cool idea, actually. But is it science?
Like
I don't know.
that NASA video that I'm talking about. They made it like last May, and it took them like I think a week to like compute everything to get so much CPU power.
I'm sure it was very
But
beautiful.
I bet you like
Yeah.
they threw away like a whole lot of it too.
Yeah.
Like
Yeah.
the last image that we got of the actual black hole.
Well, were you here for the class? We picked apart the black hole image. All right.
You said that we threw away like a lot of the images
Uh,
that created it.
9,999,999 pixels for every one that was used. So
Yeah.
I'm not sure we really have a picture of a black hole. Yeah.
I was gonna say with that picture,
Oh.
I thought it was in the textbook, but I was reading this week's assignment and they have it.
Oh, they do? Okay. Okay. All right. Yeah, it's, I don't know. I don't need to beat that horse anymore either. Yeah, Sandra.
We were talking about the galaxies and the helium sheets, it was drawing to mind like a placenta, womb with a baby and kind of the substrate in it. And then that brought multiple times now it's brought to mind the like image of little fish eggs on a rock just kind of swaying.
Wow.
There. And it does seem like more of the branches of science should be involved in pondering this.
I love it. Yeah, I tend to agree. I actually tend to think a lot of the problems in all of these disciplines come down to people being really hyper-focused on one little thing. You know, there's a really old meme in cell biology, I think it was, but it's like all these blindfolded scientists, you know, holding onto different pieces of an elephant in the cartoon, right? And they're all saying, like, the guy's got the tail of the elephant. He's like, it's a snake. And, like, someone's got the leg, and they're like, it's a tree. And I think it's a little bit like that. If, especially the more technical and the deeper we get into these fields, like you study for maybe a decade or more to be able to work one of these telescopes. You know, you don't have a lot of mind free for evolutionary biology or something like that. So. And they're all going to different conferences, publishing in different journals. It's a really interesting problem. It's almost like in our modern age, we've generated more data than we can possibly glue together. Like there's just reams and reams of data coming out of these telescopes, and that's just astronomy. And then same thing's happening in biology with genetics, right? There's so much information, the ability to knit it together. And there's some hope maybe AI could pull that off, do some of that knitting, but haven't really seen much of that yet, unfortunately. It's not beyond the pale of possibility, I suppose. What else, guys? What are we thinking about? Levin.
The black hole image.
Yes.
I'm not saying it's real, but like I heard that the reason they throw away so much data is because like they basically scanned a very large area, trying to find it. So they're doing most of it.
Yeah, I mean, the baseline resolution, when you set up these like diffraction, so they had telescopes on either side of the sea, essentially, which sets basically the diffraction window for how you can, basically how much resolution you can get. And the signal noise on that was essentially 1. So at the resolution that image, that structure is supposed to be found at. So I don't know, it seems like pretty bad science to me. But again, I think that these people, I think they've entered into the project 100% convinced that the only way to explain what they see is that there's a giant black hole there. Therefore, whatever steps they need to take to be able to generate, to image this with the preconception that that's what's there is somehow okay. But I don't think you can do that in any other science. I'm not aware of any science where you can cut data points to that degree. You know, generally speaking, if you drop data points, you have to give a long explanation for why in the figure. This is far, far, far exceeding anything that I've ever heard of, even close, by orders of magnitude in any other science. Pretty wild. So, you know, and actually in my mind, it's like, even if black holes turn out to be these incredible magical entities, and you know, we send Kevin out there in his spacesuit and he travels to another galaxy and it's just this incredible thing. I would still say that what was done with that black hole image was kind of a disservice to that theory itself too, because the last thing you want to do is do a bunch of junk science on a potentially really good idea. So, I don't.
Because like so much money and so much time and effort gets thrown into that, and then just to be like, hey, we created this artificial thing that we think this is what it's like, gonna cumulatively.
Yeah, no one's going to be proud of that 100 years from now, no matter what.
You've educated me on this a lot more.
Nice.
I mean, like, the subject way before now, and now I feel like I definitely back up your idea on it. So much time, so much effort, so many people have so many ideas that goes into it. Like that other study that got done on it, that actually took all the raw images and did their own study on it, and showed what it actually should have looked like or what they got.
The Japanese group, yeah.
Yeah, the Japanese group, I feel like that's so much more educational than what this other group did. And they're the one that actually got it published.
Right, so it's almost like no matter what comes of all of this, right? Like, if everything I'm saying is wrong, I presented to you guys 2 very different stories for the universe. Like, if for some reason somebody proves somehow that we can make black body spectra from gases, and the stars turn out to be gases, and you can collapse them and make black holes and all of this, well, those people in the future are not going to be very happy about these people like hacking together these images, because ultimately, even if they do get an image of these things, which I don't think they ever will, but if they do, they're going to not look like that, because that's not a real image of anything, honestly. So I just think it's kind of a disservice to the entire enterprise, is I guess what bothers me about it. Not necessarily because they got a picture of a black hole. It could have been a picture of a leprechaun for all I care. It's just not good science. So I don't know. It's just sad because there's a lot of, look, we live in a really like politically divisive world right now. Science is always getting attacked, you know, and oftentimes for good reasons. Sometimes scientists do really shady stuff. And I think this image of a black hole is a great example of that. Does it really affect anybody on Earth? Not really, but it kind of makes the whole thing look bad, if you ask me. So, yeah, I don't know. It's more of a meta issue again than in the particulars, because whether or not there's a black hole at the center of the galaxy isn't really going to change, you know, my weekend at the end of the day, or yours for that matter. But
I'm losing sleep over it. I don't know what to do.
I'm pretty deep into it, actually. Yeah, probably losing more sleep than you guys. But you know, it's more about like where we put our trust in these institutions, because I think that trust is kind of like the real currency that drives everything. You know, people often talk about. If any of you guys in any of your classes talked about like the collapse of empires or anything like that, you know, it's often asserted, like there's always these very like material arguments like, well, they just exceeded like their material capacity to generate power or whatever, like they chopped down all the forests, or they, you know, abused all their slaves or whatever it is. But I think they're kind of like, those arguments kind of miss the point, which is like, what really keeps a society together is trust. Like we can trust that the people who are doing the doctor job are doing a good job at doing the doctor job. The people who are doing the science job are doing, the police are doing a good job, everybody, right? It's like, you have to have trust in your society at each level. And so, like these kind of misbehaviors like that with these like data image fabrications, they undermine the trust in those institutions that we might really need at some point, right? And that's just super tragic to me. So that's why I get all worked up about it. Not necessarily because it really matters whether there's a picture of a black hole or not. So, okay. What other thoughts we got? Anything? I think that kind of brings us up to where we're at. All right. So I got my, try this out today so I can not stand behind this desk, which will be kind of nice. All right, so let's work our way towards this redshift business, because that is what we need to put this cosmology together at the end. I thought I would just maybe start here by reading you this little bit that I found on Wikipedia about what we're going to talk about today. It says, the current era of star formation is expected to continue for up to 100 billion years, and then the stellar age will wind down after about 10 trillion to 100 trillion years, as the smallest, longest-lived stars in the visible universe, tiny red dwarfs, begin to fade. At the end of the stellar age, galaxies will be composed of compact objects, brown dwarfs, white dwarfs, and the cooling or cold black dwarfs, neutron stars, and black holes. Eventually, as a result of gravitational relaxation, all stars will either fall into the central supermassive black holes or will be flung into intergalactic space as a result of collisions. So that's the future of the universe, according to Wikipedia. That is essentially the doom and gloom story that we have as our standard cosmology today. And so I kind of wonder how we got there. Well, I don't wonder. I have a story to tell you of how we got there. But in some sense, I think it's a deep reflection of our skepticism about our own material existence here on Earth right now as well. You know, people are terrified of World War III, climate change, everything else. I think we have a very doom and gloom outlook on the future as a world culture. So with that in mind, let's look at the reason that people have come to think that way. So there's a couple models for how all of these galaxies formed. Now, one thing that's worth keeping in mind before we even get into the details of this is that the standard idea, given that we've only had, I know, does 13.8 billion years seem like a long time to you guys? Who thinks it's a long time? Who thinks it's kind of a short amount of time? I do. All right. So 13.8 billion years is actually only long enough to have formed one set of galaxies. That's where things get really interesting. So the standard story that we're going to be pulling apart here is that all these galaxies formed essentially, more or less at the same time. Some of them are more matured than others. We're going to talk about some collision models, some merger models, things that could lead to the different types of galaxies. But the basic premise is that since we only have 13.8 billion years to do this, it only happened once. So what is that? The standard idea is very much this idea that we inherited from the 1700s, which is this same way that we talk about the solar system forming. It's called the monolithic collapse model, and it's essentially a gravitational swirling, just like the figure skater, who basically all this mass comes into the center, the spin picks up, and you get something that looks like a galaxy. And essentially stars, as they kind of get used up and drift as they age and so forth, some of them will drift outside of the main piece of the galaxy. And, basically all these galaxies are evolutions that happened once, ever. Which, I think that's an interesting situation, because what I'm trying to point out is that this old Kantian idea, it's only really enabled by the cosmology that says that our universe is 13.8 billion years old. If the universe is 30 billion years old, well, then you have more time to imagine how these galaxies could have emerged in second or third generation versions of themselves. If you have 100 billion years, well, then you can have a really interesting cyclicity to it, sort of like the one that we talked about with the stars, right? Where it's thought that our sun is perhaps the second or third generation star. It's got all these heavy elements in it that you can't explain with the standard model of fusion from your textbook. So if the universe has no birthday at all, you end up with a totally different situation as well. So boundary conditions, constraints on our imagination. There's also another model, which is this multiple merger model. This is kind of interesting because there does appear to be galaxies that are rushing towards us. So we talked about Andromeda when we were doing the mythology, and we looked at some cool pictures of the Andromeda galaxy. The Andromeda galaxy is actually rushing towards us right now. We know that because it's blue shifted quite heavily towards us, right? So what's going to happen? Well, the idea is in a few billion years, the Andromeda galaxy is going to smash straight into the Milky Way. Now, smash might not be quite the right word because there's a great deal of distance between each one of the stars. It's probably not going to result in a bunch of stars smashing into each other, but they will merge at some point. And so, at least if the blue shift is to be taken as motion. Now, we've seen some remnants of what we think are mergers in the past. So, what does this look like? We see these little streams of gas and dust that extend from these satellite clusters that are outside of our own galaxy and outside of other galaxies as well. So the idea is kind of when a galaxy goes past our galaxy or past another galaxy, that it sort of will strip off little chunks of things as it passes. The same thing is probably true when we were talking about solar systems as well. If the solar systems pass too close or a big star passes close by us, well, it might rip off a planet or two. We obviously can't see the remnants of that as easily as we can see these streamers from nearby interactions. So I guess to date, astronomers have found 12 tiny little galaxies that have gotten too close to the Milky Way because they can trace these little streamers back. So these are kind of like little dwarf galaxies that kind of hover outside of us. ever so slightly. See this in other galaxies too. This is actually a picture of a elliptical galaxy. Oh no, sorry, this is a globular cluster just outside the Milky Way. Again, this is supposed to be the nucleus of one of those little baby galaxies that stripped off some of the pieces from our own galaxy as it passed by, and it's kind of been captured as a little satellite at this point. But we actually see evidence of other mergers happening. Let's see here. So this is actually not one of those, I'm sorry. This is actually supposed to be a prediction of what Andromeda is going to look like as it comes close into the Earth in the future. So this is supposed to be a projection of about 4 billion years from now, when the Milky Way crashes into Andromeda. Apparently Andromeda will be quite bright in the night sky at that point. I don't know. None of us are going to be here in 4 billion years to find out if this is true or not. But certainly does seem to be heading our way. There are some really cool galaxy mergers that you can check out. One's called Stephan's Quartet, I believe. It's very beautiful. There's several of these galaxies that are kind of joined up in the night sky. I wish I'd pulled a picture of them now at this point. But it does seem that galaxy mergers is a thing that happens. And, you know, it's actually really interesting that that you would have these mergers happening, especially considering, you know, the universe being presumably so young that these galaxies must have just formed and now they're smashing into each other. This is really interesting. Okay, so the first person to really try to make, so we got to talk about Hubble a little bit. So there's this gentleman named Hubble. Most people probably just know the name from the huge telescope that was popular before the James Webb, named after him. But this guy, Edwin Hubble, was a really foundational astronomer once we started building these huge reflector telescopes back in the 20s and so forth. Really the first time that we started seeing individual stars in the Milky Way that were far away, things like that. Being able to resolve some of these little clusters outside of the Milky Way. Hubble was behind all that. And Hubble actually came up with the classification scheme that we essentially use today. Now what's interesting is that if you look at this classification scheme, it almost looks like an evolutionary timeline, right? It looks like you have a little ball of nice circular spherical star matter stuff, stars and gas and everything, and then it sort of, as it evolves, it kind of chooses one of these paths to go down and so forth. And this was actually indeed what they thought at the time. This is actually not what people think anymore. Nowadays, we actually think that these ellipticals over here are the results of mergers between spiral galaxies, and that they're actually older. And that's mainly because they have more red stars in them, it seems like. They don't have very much gas or dust, so they don't kind of have the precursors that we would think of as necessary. Whereas the spiral galaxies seem to have all the blue stars, they got a lot of dust and gas. And of course, we live in a spiral galaxy as well, so this is thought to be, in some sense, fresher and more active. So what people think now is that this timeline kind of runs in reverse, actually, and that as the galaxies kind of wear out or crash into each other, they end up more like the elliptical side of things, which is an interesting reversal of thoughts. And we'll come back to Hubble in just a second. Again, so we're looking at a galaxy here called M100, which is got all these blue stars in the arms of it, right? Which we think of as young, high-mass stars. And you can see all that dust in the plane of this galaxy too, which is really quite beautiful and thick. And you don't see these in ellipticals. So if we go over, let's check out an elliptical. So if you go over and check out an elliptical, they're redder. You can see that by eye, basically, which are those population 2 stars. They're kind of oldish, dying stars. The interesting thing about these ellipticals too, and I think the reason they think that they're from mergers is because the stars don't all rotate in this nice plane together. They're not organized. They're kind of all rotating, you know, around the center, more or less, but sometimes in different directions. They're just kind of a mess in the way that they orbit the center. I think that this story is a little bit undone so far in terms of what these things actually mean, because there might be completely different processes at play in generating an elliptical than generating a spiral. And if we don't understand what holds the spiral together in the first place, a la this dark matter discussion we've been having, we might not understand what it is that keeps an elliptical from having that same shape. So, yeah.
What's the different ages in between these? So an elliptical and a spiral.
That's a really good question.
Right?
Yeah, we are. That's a really good question. Can somebody Google that, the age difference between ellipticals and spirals, and tell us about it? Somebody got their Google open? Let's see what they say. That's a good question.
And I'm like starting to think like if maybe like dark matter has anything to do with that because it's like it's not something that we can see. Or...
Well, that's what I'm saying. Yeah, if we don't know what holds our galaxy in the shape that it has, then it's going to be hard for us to make a really reliable statement about the differences between these very different types of galaxies. What'd you get?
Oh,
Okay.
I don't
Okay.
know some. I'm trying to add on to this.
Yeah. Hold on one second. Hold that thought. Yeah.
Ellipticals are typically older.
How much older?
Average age of spiral galaxies 500.
500 million? Okay. Pretty young.
Ellipticals are between 7 and 10 billion.
Whoa. Okay, so ellipticals are almost, let's say, half the age of the universe or something like that. Okay, what were you going to say?
Thank you.
Like, since we can see that they're like either evolving or growing into different stages, is it possible that the like collision of like other galaxies or even like clouds of like gas? Because right now there's a like gas cloud orbiting our galaxy, Smith's cloud, right? Is that still a thing or?
I mean, we have got gas clouds all over the place, first of all. But yeah, these streamers are supposed to be gas clouds that kind of connect our galaxy in some sense to the satellite galaxies.
Is that the collision of that, does that form like maybe like a step into different like stage of a galaxy, or is it just like, okay, new stars, let's go on to the next one?
Yeah, like can one galaxy turn into a different kind, basically? I think that's the story that's bubbling. The funny thing, the kind of annoying part about, or not annoying, but the obnoxious piece of this, the way this course is organized, is that we know the most about the things we talked about in the first couple of weeks. We know the least about the things that we're moving into now. And so these definite answers about these things, you really wandered into these theoretical spaces where people are trying to come up with explanations for what they see, and that, Hubble's, if we go back to Hubble's original evolutionary conception of these things, it didn't work out, right? And the reason it didn't work out seems to have been largely because these didn't seem to be younger based on the fact that they don't have blue stars. And we think of blue stars as being the hot ones that haven't burned out yet. And so people moved on from that. And they've tried to explain these in terms of mergers, their chaos in terms of mergers, things like that. But there might be other explanations for how that happens. They might be able to bleb off from existing galaxies, exactly like little dwarfs or so forth. I don't know if they're larger by size. Can somebody else Google that too, if the ellipticals are bigger or they're roughly the same size as the spirals? There's certainly in these pictures they seem smaller, but I don't know that that's actually true. I'd be curious if somebody wanted to see if their sizes are different. Because, yeah, that would support, I think you're kind of pointing out a theory of them being, in some sense, little babies of the bigger spiral galaxies, which is an interesting idea. I like it.
Galaxies are generally larger.
Larger? Oh, wow. Okay. So, not so much babies. That probably supports the merger model. Interesting. Now, there's these other galaxies, too, which are kind of halfway in between. They're called irregular galaxies. And these actually contain both population 1 and the old population 2 stars. This is actually like the Magellanic Cloud and the small Magellanic Clouds. These are the little satellite galaxies around the Milky Way.
Elliptical have 10 trillion stars.
How many does the spiral got?
There's a lot to explore here.
So when it comes to, this is the other thing that's kind of tricky too, is when it comes to saying how big these things are, it's not necessarily as clear cut as it might seem. So how do we estimate the size of a galaxy?
Billion to 1 trillion.
A billion to a trillion,
You don't have 10 trillion.
10 trillion.
Yeah.
That's a lot.
Those are just massive.
Interesting. That's really interesting. Yeah. So that supports the merger idea that you have to smash a couple of
Well, it's like
spirals
all-
together. 10 of them.
Yeah. It's crazy.
10 of them. Yeah, it's pretty wild. So how do you figure out how big a galaxy is? Any ideas?
I guess you just have to measure it perspective.
Well, it's really interesting. Okay. So yeah.
Could you do something similar to like how we measure the size of binary star systems? Of taking something on one side and taking something on the other, or I guess that wouldn't really. make
Yes.
sense.
Yes, 100%. So you look at the rotation, basically.
Yeah.
So just like we talked about how all of our masses generally for star systems come down to the motion of the stars involved in the orbits, right? You basically, without beating you guys with the math of it all, you can essentially use the orbital dynamics and Newton's laws and Kepler's laws to rederive how big the things are that are orbiting each other, right? Generally speaking, things that are really big and close by one another orbit really fast. And it scales accordingly. The interesting thing is, so exactly like what Mia is saying, we can see how the galaxy is spinning by how it's blue shifted or red shifted on either side of the rotation, the angle that you're looking at. We can see these things moving based on essentially the spectroscopy, how these spectra are shifted in motion. But what's really weird is that we know, and that allows us to generate something like this. I think I pulled this from your textbook, which is, this comparison of masses between the different types of galaxies. But what's really weird is that we also, at the same time, have to acknowledge that our own galaxy does not appear to be rotating based on gravitational dynamics. That is the dark matter problem, right? If the galaxy moved based on gravitation, in other words, on mass, if mass was able to tell us how the galaxy rotated, we wouldn't have a dark matter problem. We wouldn't have a galactic rotation problem. So it's an interesting little blind spot in this whole thing, because if we're saying that the galaxies have a certain mass based on their rotation, we're also saying that our own rotation doesn't make sense based on the mass. There's a great deal of uncertainty introduced into that argument. So it's it's very much the edge of what's understood at this point. So oftentimes we'll use those, let me go back to that for a second. So oftentimes we'll use those estimations of mass, and then again, we can see how bright something is, right? We can do this to get the actual luminosity. We'll incorporate the mass estimate that we got from its rotation and its motion in order to specify exactly how many stars we think are there, therefore to say how close that light is to us based on how big we think it is. All these things could be wildly subject to variation in the future depending on how we come to understand how galaxies move more appropriately. We don't know if ellipticals have the same sort of, well, I'm just going to keep calling it the dark matter problem, but we don't know if it has the same issue with cohesion that we see in our spiral galaxy. It very well may. That those classes of galaxies may suffer from that as well, or they may not, and then we're looking for something more specific to ourselves. All right. So, in order to work towards this idea of the motion of the galaxies, one thing that we have to be able to do is be able to say how far away the galaxies are. So, let me just review that one more time. I think we know how big the galaxies are by their motion, particularly their rotational motion, right? Which, take it with a grain of salt because our motion doesn't necessarily correspond to mass in our own galaxy. If we know how big they are, then we can say how actually luminous they are, not just how apparently bright, but how really how much brightness they have. Okay, that's important. The next question becomes, how far away are they? And so we talked about a couple of ways to figure out how far away stars are, right? We talked about if we got stars that are really nearby us, we can use the parallax method, which is a pretty direct way of triangulating the distance to something. The same method that surveyors use, right? And if we got something that we can see a pulsating star like a Cepheid, and we can parallax our way into understanding how close a standard Cepheid is, then when we see a Cepheid far away, like in one of these satellite galaxies, well, we can deduce basically how its brightness is falling off, and we can figure out how far that is. When we're starting to look into other galaxies, we can no longer really see certainly can't see parallaxes, but we can't even really see Cepheids at a lot of these distant galaxies. So what do? We have to maybe look at supernova at some point, because supernova are enormously bright. So here's a picture of a supernova, and as you can see, it's basically brighter than this entire galaxy right next door to it, right? So this supernova is happening in I wish I could stand up on this desk and point to some of this stuff here. So these are galaxies, these tiny little things. Those are galaxies just as big and developed as this one. And this supernova is happening in one of those galaxies. So a supernova can outshine an entire galaxy, essentially, right? So supernovas make really good standard candles. The problem is, there's galaxies in the background of this that are so far away, we can't even resolve the supernovas of them. So at some distance, we're basically completely beyond being able to even look at, let's see here. Yeah, at some point, we've moved beyond the ability to do parallax measurements. The Cepheids don't even work for us. And the supernovas will only get us out to about 11 billion light years. But our satellites, our telescopes, like the James Webb, can see out to 13.8 billion years. So how do we measure that last little bit? And the answer comes down to what we're going to call Hubble's law. So in order to kind of make up a story about what's going on as we look back in time, we have to know how big things are, we got to know how bright things are, we got to know how they're moving, and we have to know how far away they are, because that's what ultimately leads us to this Big Bang story that we're kind of approaching very rapidly. So again, I think I've showed this at the beginning of the class to some extent, but the way that we build out our distances is increasingly abstract, right? The parallax is a very direct measure of distance. Cepheids get us pretty far. And then at some point, we have to get into things like supernovas. I'm not going to get into these other motions, but they're very similar to the rotational dynamics we talked about. And then once we get really far out here, we need to start thinking about redshift. So what do I want to say? How am I going to introduce this? So something kind of interesting happened back in the 20s. People were finally able to see galaxies that were really, really, really far away. So, hundreds, maybe hundreds of millions of light years away. And what they noticed was that the ones that were really far away seemed to be redder than the ones that were close by. So this was, I think, quite shocking at the time. And Hubble, I'm going to skip this slide and just show you the actual data first. So actually, if you take the reddening and you treat it like it's actual recession velocity, so it's something moving away from you, like the Doppler shift that we talk about, you can essentially, oops, I don't even have an axis on here, that's awful. But essentially, this is the distance away from us, right? And the basic idea is that not only are the things that are far away redder, so that they're moving away from us, but they seem to be moving away faster the further away that they are. The redshift is even more intense. Now, the interesting thing here, and we can't really skip over this too much, is that at some point, very quickly, Hubble published his relationship in the 1920s. Within a couple of years, and he didn't know what it was, by the way, so Hubble was kind of like, it's kind of interesting the galaxies that are further away are redder. We should try to figure out why that is. Very quickly, his name is Georges Lemaitre. he was a Belgian priest and a mathematician. He was studying the work of Albert Einstein, who was just coming into vogue at the time. And he deduced that if we treated the reddening as an actual motion of these galaxies, that since everything seemed to be moving away from us under this hypothesis, that at some point everything must have been really close together. And so he essentially gave us what is now considered to be this expansion idea, which eventually led to the Big Bang itself. Now, it's interesting because Lemaitre published this work, and it was, I think, not very well known initially. Actually, the Pope loved it, and the Pope started talking about how it was proof of the, creation of the universe in the very early days of Genesis. And Lemaitre told him to basically shut up because he was making him look bad. He was like, no, this is science. This isn't church stuff. But at any rate, it was for whatever reason, this idea completely caught fire. Now, I don't know if it caught fire because people really wanted a creation story, or if it caught fire because nobody else could think of a good reason why the galaxies far away should be red. Can anybody here think of a reason why the galaxies that are far away would be red that doesn't have to do with their motion? This is like a expert level question. What's up?
Liquid model, right?
Well, maybe. Actually, this doesn't have anything to do with liquid stars. That's the one thing that doesn't, yeah.
It's just like distortion, because you can't see it as well, they're gonna.
I mean, in some sense, I think that there's an argument to be made. What kind of, so if you think about, this is maybe a little too advanced of a question for you guys since you're not really science majors or anything. So red light is actually really low energy compared to blue light. So the bluest light, like bluer than your eyes can see, is like X-rays and gamma rays. That's like really, 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 really blue, burn your face off light. Really red light, on the other hand, is like radio waves and like light you can't even see, it's so red. Infrared, stuff like that, right? It's low energy, actually. That's why we can bathe in all of these radio waves and our bodies don't just cook, right? So needless to say, the light coming from these distant stars is really low energy, right? And so an alternative argument that's been kicked around for the entire last century since Lemaitre proposed this recession idea is that, wait a second, what if all that light traveling across 14 billion light years of distance, what if it just loses energy as it's relayed across that vast distance, right? This is called tired light. And it's been very seriously entertained in different eras across the last 100 years. There have been several proposals that were taken very seriously. There was mathematical arguments made for and against it, and many of them are still on the table and being debated today. So, I understand that, one interpretation is that galaxies which are very red in the distance could be moving away from us. Another possibility is that light, which is traveling across unimaginable distances and being relayed between countless atoms along the way, loses energy due to just transactional losses, right? It's kind of like, if you had friction in a system and you were just bouncing, like a water wave in the ocean, right? If you make a wave in an ocean, it doesn't go forever, right? It actually lengthens over time. You may have tried this in a pond or something. You see the waves actually spread out over time. Why do they do that? Why do the wavelengths get redder in the water? Because lengthening is the same as reddening. Because of friction, right? Because some of that energy of the water molecules pulling on each other just takes the life out of the wave eventually over time. So, no one has succeeded in providing a convincing mathematical argument for how this could happen, to my knowledge, at least at the moment. It's certainly not in vogue. It was at some point in the 1980s for a while. But these tired light proposals pop up all the time. And they're quite intriguing, actually. I tend to lean towards them myself. But what's even weirder about all of this is that this proposal, that the galaxies are moving away from us, that is the diet version of what we have today. So again, it would be one thing if the galaxies that were really far away from us, I think this is actually redshift on the bottom. The galaxies that were closest to us, if those were less redshifted and the ones that were furthest away were more redshifted, that would be one story. And that's kind of where it started with Lemaitre and Hubble. But what's actually recorded is that it's nonlinear. The ones that are farthest away have a way bigger redshift than the ones that are closer. And it's not just like something that's 2 units away has twice the amount of redshift as the one that's 1 unit away. It's actually much more than that. So, what is the explanation for this? Well, you know, somewhat unironically, the idea is that the space itself is expanding throughout the universe in between these galaxies. I think this is from your textbook, which is, I thought this is a really interesting thing because, you know, as you can see, the ruler is expanding, but the ants aren't expanding. Just the space, right? Because what is space in mathematical physics? Space is really comes down to a coordinate system for defining the locations, so the distances between different bodies. And so what do they mean when they say that the space is expanding? Well, that the distance between the bodies is expanding. It's kind of an interesting circular argument. It's not. It does appear to be the case that these redshifts are enormous at these distances, but whether the distance between them expanding is an explanation for what's happening seems a little bit off for me. You know, it comes down to again this idea we started class with, which is like, what's the difference between math and an explanation for what's happening? They're very, very compelling mathematics that have very little explanatory power to them. You know, I always really shudder to use the word proof in science in general, because proof is actually a logical statement. It comes basically from mathematics, where you say, you know, if this, then that. If I have 2 quantities and I multiply it by 2, then I get 4 quantities. And there's ways to prove this mathematically just using logic. Science isn't really so much like that. It's like you make some assumptions going into it. In this case, we make the assumption that the reddened galaxies are moving away from us. That's an assumption, right? That comes down to whether or not you think that redshift is purely due to motion. If it's due to some other process, then everything that follows downstream of that statement is going to be broken. So in this case, space expanding and the universe expanding, it follows downstream from accepting that the galaxies themselves are moving away in the first place, which they may be and they may not be. Jury's still out as far as I can tell. As far as the space itself expanding, this seems like a little bit of a non-explanation to me. I mean, you know, again, can you apply physical processes like warping and expansion to ideas, right? Like, can you, is it proper scientific language to apply a physical process to an idea or to a concept? Like, space is a concept. It's a system of measuring distances between objects. Can you apply physical processes to it? Can I apply physical processes to love, which is another concept? I don't think so. I think you can really only warp materials, and you can really only stretch materials, not so much ideas. So there's some circularity to that. All right. So this is all leading up to a discussion, because there are basically 2 pillars to this Big Bang theory that we're going to be starting to play with. And there's 2 pieces of this puzzle. There's actually a couple of other little pieces, but I think there's 2 main legs to this monster. One of them is this redshift distance relationship. So, in other words, things moving faster as a result of redshift. Let's just say redshift higher at a distance, converted into this expansion idea. There's another one which we're going to be dealing with next week, or maybe on Thursday, I guess, which is called the cosmic microwave background radiation. What's really interesting in cosmology right now, and what has everybody really freaked out, is that when you calculate the age of the universe based on this redshift business, you get one age value. And you can calculate it very precisely. You can basically take all of these galaxies, get their redshift, and trace back this metric, and you can come up with an age at which all of those things converged based on these expansion dynamics. You get an age for the universe. We haven't talked about the CMB, but we will. When you calculate based on the CMB, the age of the universe, and we'll talk about how to do that, you end up with a very different value. And those values are different, and they're different by several standard deviations. So if you have two populations and you want to say whether there's actually two separate populations or not, you can see how big the spread is on those numbers. These spreads are completely not overlapping with each other. So each one of these methods is extremely precise, and it doesn't give the same value as the other one. This is what's called the Hubble tension in cosmology right now. And it's a huge part of the reason why people think that there's going to be some sort of new model that comes forth. You know, this is, of course, married to the observations of the fully formed galaxies just a few 100 million years after this supposed birth of the universe moment. There's a lot of things, there's a lot of tensions inside of cosmology, but I think the biggest one is actually, from a numeric standpoint, is actually the disagreement between the age that you get from this Hubble redshift relationship and the one that you get from the cosmic microwave background radiation. I am going to save the CMB for you guys for next time. What do you guys think about this? How do you feel about the expansion of the universe? What about expanding space-time, things like this? How does it sit with you?
Seems right.
Seems right. Kevin's on it. He's going into the black hole. All right. Yeah.
I feel like the concept's gonna happen no matter what. Like, you can't just sit there and be like, oh, I don't like this.
Well, you can say that the galaxies are red. That's the thing about all of these towers of assumptions, really. You have a primary observation. The galaxies are red. Now, that the galaxies that are red, does it mean that they're actually moving at all? I don't know. I don't know. I certainly think there's probably other ways for them to be red besides the fact that they're flying away from us. There's other problems, too. I didn't even mention this. I'll get to you in a second, Mia. So there's blue-shifted galaxies, too. This is kind of weird. So, like I said, Andromeda is coming straight towards us, right? A number of galaxies are actually heavily blue-shifted and flying straight towards us. So these are thought to be kind of exceptions to the rule. There's also these really weird, remember we talked about quasars a little bit. Did we talk about quasars a little bit? Not really. Okay. So these jets that are shooting out of the center of galaxies, we'll get to them. Some of these seem to have an intrinsic redshift to them. So even though the galaxy is, say, turned such that the jet is facing us, these jets of material that are flying out of the center of these quasars are also redshifted, which makes no sense because they're doing the same thing that these galaxies far, far away are doing, but they're clearly shooting stuff straight at our faces, basically. And this work was done by a guy named Halton Arp, who was a graduate student of Edwin Hubble. And he published a huge book called, I think it's called The Encyclopedia of Peculiar Galaxies or something like that. And it still, to this day, stands as a very strange piece of the puzzle because there does seem to be ways that things can be redshifted as a whole that has nothing to do with their actual proper motion. So, when you say, we can't deny what seems to be apparent, right? I think Jasmine, I think you're right about that. I think that we do have to acknowledge, but the only thing that we know that's apparent in this case is that those distant galaxies do appear to be redder. Now, why they're redder, that seems to be a big piece of the puzzle. And whether you subscribe to the fact that they're redder because they're moving, or they're redder because of some other energetic losses process, or something intrinsic like with the quasar jets, you're going to come up with very different models for what's happening. What were you gonna add?
I think that ties in really well with what I was wondering about. I could have a simple answer, but I guess the more we've gone into it, the less and less I'm convinced that the stories we're telling are fully accurate. Because if all the galaxies are moving in like a similar direction or just outward from a center point, then it doesn't really make sense to me how Andromeda is coming towards us. But like you're saying, like the blue shift, like they're actually coming at us instead of away from us. But I guess I don't understand how, if the force was so great to like push everything out, how something could counteract it to the point of it moving in the complete opposite direction. So not just slowing it down, the stopping point, but redirecting it without affecting anything else.
Yeah, I'll try to look up the standard explanation for it. I'm sure there is one, first of all. But yeah, there are serious contradictions. I actually think that Halt and Arp stuff is probably the most damning of the whole story, because he's talking about galaxies that have these super, like the jets that are coming out of these galaxies that are shooting out of the center of them. I think we'll talk about this process at some point here very soon. They're moving at like ultra relativistic speeds, like fractions of the speed of light, just like particles just streaming out of the center of these things. And these things are pointed directly at us, and they're redshifted heavily, sometimes like big redshifts actually. So we know for a fact that there are processes that can generate redshifts that have nothing to do with the motion of those bodies. And so, you know, at least at the bare minimum, we have to keep an open mind that there might be processes happening in those distant galaxies that or intervening in between us and them. Again, these are the farthest things that we can even see with telescopes. Think about I mean, it's hard to comprehend the distances that we're talking about here. So I think there's ample opportunity for new processes to be occurring that we just haven't understood yet. I think that it's kind of it would be a little bit, there's probably a French word for this. It would just be, I think, a little naive to assume that the only possible explanation is that this is a Doppler-type recession velocity. It just seems like, well, that might be the case, but there's probably a gazillion other processes that we should investigate as well before we just leap to that conclusion. Especially because the story you get from using the redshifts versus the CMB, they're not congruent stories. They don't tell the same story. And that's a huge problem, and people recognize it as a huge problem. So, yeah, I mean, but again, guys, like, you know, we have reached that point in the story of the universe where we are very, very far away from our own sun, you know? And if we misunderstand our own sun as poorly as I suspect we do, you can only imagine how poorly we understand things that are, you know, billions of light years away from us. So, yeah, let's talk about these quasars next time. Let's talk about the CMB, and let's see if we can make sense of all the possibilities together. Have a good week, guys. See you next time.